Africa. Energy has always been an important area of focus for the mining community. This focus has only increased in recent years. For many, the topic of energy is increasingly impacting our personal lives, from backup power from our homes to the prospect of electric vehicles. Karmakai works with various technology partners to bring value-adding solutions to the mining sector. Understanding this technology and the potential benefits can at times be somewhat confusing and possibly daunting. But I hope that through this short presentation, I'll be able to at least give some high-level insight into this area. Today, I'm going to run through some aspects of energy generation and some typical cost-saving approaches. We will briefly look at some of the terminology used when discussing energy systems, explore a few generation technologies, and touch on storage technologies. I will then discuss some areas of application and opportunities that may present themselves for your business. Finally, I will suggest a few thoughts on finding and implementing cost savings in the operational environment. Almost on a daily basis, we are presented with news articles, press releases, or discussions around electricity or the lack thereof. Locally, the ability of our national utility to keep the lights on and the cost of electricity have become an ongoing part of the national conversation, perhaps surpassed only by the potential impact of the current global pandemic or our latest political soap operas. Since 2008, South Africa's electrical tariff has consistently increased above the consumer price index, exacting a high toll on businesses and the population as a whole. In the global narrative, the reduction of emissions and a drive towards, at a minimum, carbon neutral operation is also becoming the war cry for both small and large businesses. In this push for new ways of thinking and operation, various issues are often balanced off against each other to try and find an optimal solution. Two such considerations that often get highlighted during the evaluation of energy systems is the continuity of supply and the cost of supply. Mining operations rely on a consistent supply of power to ensure effective operation. This is best served with technologies that can consistently produce power, sometimes known as baseload or prime power units, which have historically mainly been fossil fuel based. Emerging renewable alternatives can offset some of this requirement, but typically are not effective as baseload providers without the addition of some sort of storage. Another consideration is cost. Typically, anywhere between 25 to 40% of a mine's operational cost can be attributed to energy. It makes sense then that any new technologies that we consider should reduce operational costs while simultaneously minimizing the upfront capital burden. Significant strides have been made in both of these areas and have contributed to the change of the energy supply mix in many countries. So perhaps before we dive into talking about some of the technologies and their applications, I would like to quickly highlight a few terms that I will use during this presentation and ensure that we have a common understanding of these terms. The electrical standard international unit of power is the watt and is used to designate the rate of energy transfer. Generally, we refer to generation technology in watts, kilowatts, or megawatts. In batteries, we are more concerned about how much energy is stored and therefore generally talk about its energy capacity. Capacity is normally described in watt hours, kilowatt hours. So where was I? So for smaller batteries, we can use amp hours as a measure. And in order to convert amp hours to watt hours, one simply multiplies the amp hour rating with the battery voltage to get the capacity. Many technologies have differing life cycles, maintenance requirements, and operational costs, which make them difficult to compare. The next two terms were developed as a way of trying to compare technologies on a similar basis. The LCOE, or levelized cost of energy, tries to address this by taking all the discounted costs over the lifetime of an electrical generation plant, normally 20 years, divided by the discounted sum of the actual energy amounts being delivered. This gives us a net present cost per unit for operating the unit or plant over a specific period. While a useful tool, care should always be taken in understanding the underlying assumptions behind any LCOE numbers before comparing them to different data sets. A similar measure has been developed for battery technologies and is known as the levelized cost of energy. Sorry, the levelized cost of storage, should I say. There are numerous technologies available to us today for the production of electricity. Most involve the conversion of mechanical energy into electrical energy. For the purposes of this presentation, I've chosen to split the generation technologies into two general areas, namely thermal or combustion-based technologies and renewables. In the first category, mechanical energy is generated from the driving of a turbine or engine with thermal or combustion processes. This mechanical energy is in turn converted into electrical energy. For applications requiring large power generation, steam-driven turbines are a well-established and highly efficient technology. The steam is generally generated from the combustion of fossil fuels, although nuclear and concentrated solar applications offer lower carbon alternatives to these. These plants usually have a high upfront capex component, but due to their long life and efficiency, offer very attractive operational energy costs. Where lower power requirements are needed, or where upfront costs or project duration is short, the use of less efficient combustion engine or lower grade thermal systems becomes significantly more practical. Examples of these include your ORC, or organic Rankine cycle technologies, that can produce power from low temperature streams, typically anywhere between 200 and 600 degrees Celsius. The second category of technologies generate power from potential, kinetic, and solar energy sources. Generation from renewable sources has been making significant strides in cost and efficiency, and are the focus of many companies looking to reduce their carbon footprints. Here we see some generation cost data compiled by the International Energy Agency for 2020 from the aggregated data from 24 countries. As we can see, solar photovoltaics is making very significant inroads to the power landscape. These next graphs show a comparison of the various renewable technologies. Again, we can see the dramatic drop in the solar levelized cost of energy as shown by the yellow line in the last graph. Geothermal is also an interesting and sometimes overlooked technology with a good capacity factor and a competitive levelized cost of energy. Certainly, something to consider for mines near the Great Rift Valley, or perhaps even mines with ultra deep experience. So while renewables have been making significant inroads, the main Achilles heel for the technology centers around consistency of supply. The sun only shines during the day and the wind does not blow consistently. The development of energy storage is critical for the larger adoption and sustainability of renewables in large power systems. Energy storage can once again be split into two different areas, namely chemical batteries and other battery technologies. Chemical batteries are devices that store chemical energy and convert that energy into electrical energy via a chemical reaction. Alternative storage solutions include using capacitors to store electrical charge, potential energy systems such as pump storage schemes, and even heat storage such as molten salt and concentrated solar power systems. The attached table shows a few currently available battery technologies. It is important to note that the battery technology should carefully be considered against the application, as no single battery technology is necessarily appropriate for all areas. lead acid has been the traditional workhorse of the energy storage space. While still relevant in certain spaces, new lithium-based technologies have grown tremendously, driven by innovation in the EV market or electric vehicles, large production investments, and personality influence. Supercapacitor and flow batteries are perhaps lesser known battery technologies with important and new roles to play in the energy storage landscape. When looking at batteries, some of the key considerations include performance, cost, safety, life of project, and recyclability. For those interested in learning more about batteries, I would recommend looking at batteryuniversity.com, which offers very comprehensive information on various batteries and their uses. Now that we've looked at some of the technologies, let's move on to some of the applications and opportunities. The first that we will look at is the optimization of technology and fuel. In Africa, many mines and businesses do not have the luxury of grid-connected power and are dependent on running diesel generators. These generators are fairly readily available and reasonably affordable, but in continuous use situations attract a high operational cost. A white paper presented by Inglet and Stubbs in 2019 looked at the impact of running high-speed generators versus medium-speed units utilizing diesel fuel. Heavy or high-speed units typically run at between 1,200 and 1,500 revolutions per minute, while medium-speed generators run between 700 and 1,000 revolutions per minute. The medium-speed units use less fuel and have longer maintenance intervals, but are more expensive in upfront capex than their high-speed counterparts. The study looked at two scenarios: a prime power plant of 10 megawatts and one of 30 megawatts in size. They found that on the smaller 10 megawatts case study, the site would save an estimated $18 million over 15 years. On the larger 30 megawatt case, this saving increased dramatically to over $117 million. The team at ISI then also looked at changing the fuel from a diesel fuel oil to a heavy fuel oil, which again made very significant impact on the cost of energy, primarily because of the cost savings around the fuel type. In this case, the 10 megawatt study, the cost savings increased by $48 million, while in the 30 megawatt case, the savings increased by $138 million. This example, of course, looks only at optimizing the base load technology. So what about reducing the costs using renewables? Hybrid systems are becoming more common in the mining space and refer to a system that combines more traditional generation technologies for base load with renewables and sometimes storage to reduce costs and carbon footprint without compromising on system performance. Key to a system like this is the integration and management of the different energy sources while meeting the required load demand. The savings from a hybrid system is very dependent on lots of factors, such as location, the plant load profile, and any existing power supply infrastructure that is in place, to name a few. Typically, for a PV hybrid, savings between 10 to 20% can be achieved on operational energy costs. With the introduction of storage, this can be extended to 40% or above. However, the current cost of storage does limit the penetration somewhat. Some recent examples include hybrid systems include Resolute Mining's Syama mine in Mali, which recently installed a PV and battery energy storage system. A savings of 40% cost of energy and 20% reduction in the CO2 emissions has been reported for that particular site. In another example, the addition of 35 megawatts, of a 35 megawatt solar plant and a 17 megawatt hour system of energy storage to an existing 64 megawatt thermal engine plant at B2Gold's Fekola mine is expected to save over 13 million liters of heavy fuel oil reduce the carbon emissions by an estimated 39,000 tons per annum, and generate a payback in just over 4 years. In addition to the applications just discussed, there's also opportunities to reduce cost in several other ways. In two of these, we'd look to optimize the site's power consumption, where so-called time of use or peak tariffs are introduced by supplying utilities. This is referred to as load shifting and peak shaving, respectively. Depending on the tariff structuring, there can be significant savings to be made from looking at these two options. In the case of load shifting, seen in the diagram on the left, power in the early morning and late evening is cheaper during the day. The load profile in this particular example also shows a lower demand at those times, although this may not always be the case. In this example, we would look at trying to move or shift some of the activities earlier or later in the day to take advantage of the lower rate. In load shifting, the overall consumption remains the same while the cost is reduced. In peak shaving, we introduce additional low-cost capacity, usually in the form of solar or solar-charged battery systems, to reduce the demand from the grid, with the effect of reducing the consumption. Two other areas that can contribute to cost savings are production security and consumption. The production security, I think, was mentioned in some earlier presentations. Both of these are related to an opportunity cost of production lost. Any time when the plant or site is not operational represents lost income, which can very quickly add up and is usually multiples of the associated cost of the interruption. A good example of this might be a mill or a crusher. You generally don't want these types of equipment to suddenly stop. Aside from physical damage that could affect the units, the subsequent cleanup time and restart then adds significant operational downtime cost. During a power failure, having a solution that allows the unit to get into a state where it is ready to restart can make a very good business case very quickly. Finally, I would like to suggest a few areas to consider when embarking on an energy project. Firstly, make sure that you have appropriate measures in place and good data on your system. This will not only give you an understanding of which areas to tackle first, but also what impact your changes are making. Secondly, look for opportunities for energy reduction first, and then direct the use of look at opportunities for energy reduction and direct the use of low-grade energy sources. Many businesses have already adopted this approach by looking at energy efficient motors, lighting, and heating. In some cases, different processing methodologies can also assist in this area. Where possible, look at extracting the maximum from the waste heat sources by using them directly in the process. Finally, depending on your company's strategy, look at alternative supplementary generation. I normally suggest that companies start small and get to understand the technology before going with a one solution covers all approach. For example, powering remote pump stations or non-critical infrastructure can give your team insight into the best way to structure the system within your particular site requirements. Smaller implementations also give you more flexibility and redundancy. I do hope that this short presentation has given you a bit of insight into energy and your business, and wish you every success in your future projects.